Okay, so this is a recording of the first lesson, chapter 8.1. I want to stay on schedule. The schedule says we're supposed to do 8.1 today, Tuesday and Wednesday, and then we'll finish this section on Wednesday. So for the people that are in DC, or for you guys, if you don't know how to do parametric mode on your calculator, or you don't know how to deal with motion, I want to do today examples 1, 2, and 3 in your textbook. It's 385, 387. You have the calculator there. The first task, it says, show that this velocity function, this is example 1. Oh, and by the by, as you start to work these problems, go back to your class page for a minute. I have put in your G class, chapter 8. This is all the exercises. This is out of the teacher's edition. I can't mark on there. This is all the answers to chapter 8, right? So starting with a quick review of 8.1 and going all the way through the end of the chapter. As you spend time in the exercises, and you should be doing that, there's a quick quiz, section 8.1 to 8.3. Might be sensible to do that. And there's some reviews, but all the way through to the end of the chapter. I think there were 5 pages here. You should be able to check all your work. Now, be advised, these are only the answers. These are not the solutions, right? So the solution is how you get to the answer, right? So if your answer matches these, that's generally pretty good. If your answer doesn't match these, that doesn't mean you're wrong. Remember what we were talking about, the way integrals can look differently and still be the same thing. But yeah, spend some time doing exercises and checking answers. So you have them all for the evens and the odds, by the way. Okay, this is example number 1, not exercise number 1. It says ds dt, that's velocity. And it's given as this function, t squared, minus 8 over t plus 1, and that's squared, and this is centimeters per second. Okay? And it says this is valid for t values between 0 and 5. And then it says describe the motion. The scenario is a particle moves along the x-axis. So describe what's happening. Do they tell you anything else? Does not say anything about where it starts. So even though we have some information about velocity, we have no information about where we are. So let's suppose this is an x-axis. We could be over here at 50. We could be at negative 30. We don't know anything about where the particle starts. So the particle starting at some location, which we don't have, and by the way, we cannot find. We cannot find where it starts. But what we're supposed to do is describe, what does the motion look like? Is it moving to the right, or is it moving to the left, or is it temporarily stopped? That's the exercise. And again, just by the way, the reason we can't find out where it comes or where it starts from is when you integrate velocity. So let's say the velocity was 2t, and we try to integrate with respect to t. What is the integral of 2t? squared. Well, you're wrong. Plus a constant. See, there's this constant that we don't know. And so there's an infinite number. This is a position now. Right? The integral of velocity is position. If we don't have any information, we can say lots of things about velocity, but we can't say anything about the position because we don't know what c is. So in this problem, they are not asking us where do we start or anything like that. They just say describe the motion. Okay. So your author says, let's look at a picture. So we're going to go to the calculator. Go to your calculator, and we'll dump in the velocity equation. They're using t. We're going to use x, right, because we're in function mode. So we're going to do x squared. Just dump this in with me if you could. Minus 8 divided by the quantity x plus 1 squared. Squared. Okay. And they do give a graphing window in your book. So go to window. It says go from 0 to 5 in the x direction and from -10 to 30 in the y direction. And it doesn't say where the tick marks are, but I would guess just looking at the picture, anybody want to tell me what the tick marks are on the y-axis? Look in your book. There's a green picture there. It's going from -10 to 30 every 5, right? Scale, the tick marks are every 5. So if we graph that, this is the picture that's in your text, and that gives some indication about the motion. So far, so good? Okay, so we're looking at that, and now we want to sort of talk about what do we see. Okay, so this is time, this is velocity, and according to the graph, we have something like this. Okay. Now, this seems a little simplistic, but I find it very useful for many students. This is the 0 line. This is where velocity is 0. Everything above that line, up here, this is positive world. Now that sounds a little silly. Everything down here is negative world. And if you look at the red curve, some of the time the red curve is in negative world. Some of the time the red curve is in positive world. Sometimes the red curve is sitting on the 0 line. Well, if velocity is 0, what does that mean for motion? Stopped. Okay, so let's just note that. If v is equal to 0, particle stopped. If we're trying to describe the motion, it would make sense to find the time when it stops. So let's do that on the calculator quickly. It says on, this is 1, 2, 3, 4, 5. It looks like there's a 0 between 1 and 2. Can you find that quickly, I hope? Second, calc, 0, right, between 1 and 2. And there we are, 1.2545. Okay, do I need to do that again? A, make sure you have the right function keyed in. Okay. B, put the window as they said. Look at the picture. And now you're trying to find a 0. So you're under the 0 utility is second calc. So second trace or second calc. It's option number 2. You're trying to find the 0. It says, give me a left bound and a right bound. Just by looking at the screen, we knew it was between 1 and 2. So left bound is 1, right bound is 2, and then you guess. So particle stopped at t is equal to 1.255 if we go to the nearest thousandth, which is what you should do. This is a motion problem. It does say, remember, this was centimeters per second. So we should put some time in here. This is time in seconds. And this is velocity in centimeters per second. So 1.255 seconds, right? That's when we're stopped. Be careful. If we're in function mode, right? Function mode is we're down here. We're going to go to parametric mode in just a little bit, but right now we're in function mode. And in function mode, these are y's and x's. But our graph is not in y's and x's. Our graph is in t's for the independent variable and v's for the dependent variable. So everywhere you see an x, you have to think t, right? So here's the graph again, and we found this 0, this x-intercept. And we'll try that again, Joe. Graph 0, 2, left bound 1, 2, and guess. And it says the 0 is at x is equal to 1 point. That's wrong. We don't know what x is. Time is equal to 1.255. Comments or questions there? We haven't done, I don't see any part A here. Well, it just says describe the motion. Are you in the book? So figure 8.1 shows the velocity of a particle moving along a horizontal s-axis. Oh, it says x-axis, not even x-axis. Describe the motion. So we're trying to figure out what's going on here. We know the particle stops at that time. So how about this negative portion down here? This portion where the velocity is negative. Velocity is negative. What does that mean, motion-wise? It's going backwards. Well, it's a little careful about backwards. I like going in a negative direction. Okay. Well, you know, what does backwards mean? If the particle is moving on a vertical axis, let's suppose we had something on a vertical action, we'd have to figure out what's positive and what's negative. That may mean going down, right? If we're on a axis like this, now it's really ambiguous. What is the negative direction? And you may think, well, negative is going down. Well, suppose I rotate the curve. Now what's the negative direction? Is it still going down or is it moving left, right? I don't know. So you sort of have to define what do we mean by positive and negative. I would just say moving in a negative direction as opposed to moving backwards. Okay, so particle is moving in a negative direction. So let's make that note. Particle moves in a negative direction for time between 0 and 1.255. And again, these are seconds. Note by the by, if this is our time when we're stopped, you cannot say the particle is moving at that time, right? So that's why I have this strict inequality here. Right? And for all times less than that, we know the particle is moving in a negative direction. And for all times greater than that, we're moving in a positive direction. So bigger than 1.255 all the way up to 5. We don't know any information beyond 5. We suspect it would keep moving. But this is only defined for x's between 1 and 5, wherever the equation was. Yeah, or between 0 and 5. Okay, now what else might you be interested in other than the direction of motion? What might you be interested in if you're describing motion? What might you be interested in? Huh? Okay, possibly acceleration. Say it. Speed. Let's talk about speed. Jeez. Okay, speed. Speed. acceleration. Velocity. Okay, so the velocity was given, right? Is the speed the same as velocity? No, what is speed? It is a scalar. How does it compare to velocity? Bingo, that's the key. So speed is the absolute value of the velocity. And by the by, since we have this velocity given to us, let's go ahead and graph the speed. So go to y equals, slide down to y sub 2, and throw in the absolute value. It's under the math button. Math number is absolute value of the velocity. Now I could type all that stuff in again, or I can just use y1, vars, y vars, function y1. So far so good? Now I would like to distinguish these two graphs, one from the other. Unfortunately, this calculator doesn't have pretty colors like yours does. But if I have the old school, I can actually make one of them bold. So the absolute value graph will be bold. So if I graph, I see the speed coming in. And what could you say about these two graphs? If velocity is positive, well, speed's always positive because it's absolute value, right? It matches up. If velocity and speed mean the same thing, if velocity is positive. If velocity is negative, then speed is positive. In fact, it's the opposite of it, right? Okay, so look at the dark curve here on my calculator, or the red one, or whatever color it is on yours, okay? Talk to me about speeding up or slowing down. As we're moving on this first little bit of time in here, are we speeding up or slowing down? Is the speed getting larger or smaller? Getting smaller, right? We're slowing down. So here's sort of the speed curve. It looks like this, and then it goes like that. Okay, so now this is still time, and this is now speed. And you can certainly see everything is in positive world. The speed is always positive. Well, I just lied. When is the speed not positive? Okay, and what time was that? That was the 1.255, was it? Okay, 255 seconds. So at that particular time, speed is 0. But other than that, speed is positive. It's in positive world. It makes sense. Speed is the absolute value of the velocity. What can you say about the motion in this time interval right here? So if I'm running towards the door and then I go, okay, do it in normal language. Slowing down. Okay, slowing down. That's what you want to say. So we're going to say particle slows down from, what are the times? 0 to that 1.255, right? Slows down. At 1.255, it stops. And then what happens from 1.255 out to 5? Okay, so in vernacular, speeds up, right? Speeds up. Okay, so particle slows down and particle speeds up. Okay, now we don't need to look at the speed graph for that to make sense. So let me go back to y equals, and I'll just turn this one off. You can turn it off by just unhighlighting the equal sign. There's my velocity graph. And then somebody, was it Annabelle, that said acceleration? So somebody mentioned that word. I wrote it down here. Is that you? Okay. So talk to me about what is acceleration? I mean, mathematically. Speed is the absolute value of velocity. Acceleration is the derivative of velocity, right? So this is now going to be V prime. Okay? And let's look at the picture again. We have this picture. This is T, this is V, and the graph looks something like this. I can't even draw diddly squat. Let's try it again. It goes like that. From the picture now, no analytic analysis. Talk to me about V prime. What could you say about V prime by looking at the picture? Positive. V prime is positive. How do you know? Nope. The slope is positive, right? Isn't this going uphill? Right? And a derivative talks about slope? Yeah. So when I look at this, I see slopes that are always going up. So we can say V prime is always positive on this interval 0 to 5. Okay, so far so good. Now, there's a unique relationship between the acceleration, which is V prime, and the velocity, which is V, when it comes to describing motion. Okay, you should know this. You should have had it earlier in the course. Whether or not it internalized, we need to make sure that happens. If velocity and acceleration are the same sign, now by same sign I mean positive, both positive or both negative, okay, then we have a speeding up scenario or situation. Speeding up. Okay? So, we just said by looking at this picture, acceleration is always positive, and this red line is the velocity. Sometimes the velocity was positive, and sometimes the velocity was negative. Don't you see it's rather clear, I think, that for this portion, the velocity is positive and the acceleration is positive. Acceleration is always positive. How about if velocity and acceleration have different signs, like right in here? Here, the velocity is negative, but the acceleration is still positive, right? So if velocity and acceleration have different signs, what does that mean? Not speeding up, slowing down. Yeah, so if velocity and acceleration have different signs, that is either a positive and a negative, or a negative and a positive, right? Then slowing down. Now, this is the demo I always give when I teach this, so even though other people can't see it, you're going to see it. Let's look at the pen. It's going to be moving. We'll keep your eyes on the pen. Okay? For those that weren't here, I just threw the pen up in the air. As it was rising, let's define that to be positive direction. As it was rising, is the velocity positive or negative? Positive, right? Yes, that's going up. It's the direction of motion. Okay, is the acceleration positive or negative? Negative. Why? It's slowing down, right? As it rises, we know it's slowing. The velocity is positive. The acceleration has to be negative. Okay, now when I throw it up and it comes back down, did it ever stop? Yes, it stops at the top, right? And how do you know that? Well, velocity is positive when we're going up. Hang on. Okay, so yeah, going up, velocity is positive. Coming down, velocity is negative, right? And the things that's between positive and negative on a number line? 0. So velocity had to be 0 when it turned around. Okay, so now instead of looking at the part going up, let's look at the part going down. Okay, so now we're falling. Is velocity positive or negative? velocity. Direction of motion is negative, right? Is acceleration positive or negative? Everybody says that, and you're all wrong. Acceleration is still negative. Is the particle speeding up or slowing down as I drop it? It's speeding up. You told me the velocity was negative, right? The acceleration has to be negative. They're the same sign. Now, if you're in physics class, you know the acceleration due to gravity is a constant. It's negative 9.8 meters per second squared. If you knew the acceleration was negative when this is rising, it's still negative when it falls. The acceleration doesn't change. You're in physics? Acceleration due to gravity. G, negative 9.8 meters per second squared. Okay, so yes, particles falling faster and faster and faster. Velocity is negative because it's going down. Acceleration is negative because it's speeding up. Acceleration and velocity, they're both negative. Okay. Now, what scenario might you have where the velocity is negative and the acceleration is positive? Let's imagine, this is a thought experiment. I have a helium balloon, and I have it in my hand, and I shove it as hard as I can towards the ground, right? Is the velocity positive or negative? Velocity is direction of motion. It's negative because it's moving in a negative direction. Is the acceleration positive or negative? Why? It's slowing down, right? As it drops, because it's a helium balloon, right? So I shove it down, it's going slower, 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 and then it stops. And then what happens? It goes back up. As it's rising, is velocity positive or negative? Positive. Velocity is direction of motion. And is acceleration positive or negative? Positive, because it's speeding up. Because it's speeding up. It's going faster and faster and faster, right? Now, again, you should have had that. The textbook says this is linear motion revisited. You're supposed to know this already. Okay, example 2. When do we get out of here? 19? 15? Okay. I'd like to get through both of these. Example 2. It says, suppose the initial position in example 1 is 9. Okay, so this is example 2. We had velocity given as t squared minus 8 over t plus 1 squared. And now we're given one additional fact, that the position at 0 is given to be 9. That's our initial condition, by the way. That's going to allow us to find that constant. Right? So now the task is find the position function. Okay, so this is what the last chapter was all about. We simply integrate. We can do this pretty quickly. The integral. Now, instead of v, I'm going to write this, ds dt, right? Because velocity is the derivative of the position. Do we agree with that? What are the units of the position in this problem? Centimeters. And the units of time? Seconds. Okay, so this velocity is centimeters per second. So when I write the integral of velocity, I get, this is centimeters per second. But whenever we do these integral signs, it's real important to have a differential at the end, right? So what I'm trying to do now here, let me just back up just a little bit. I'm trying to integrate the velocity. And I'm just emphasizing by writing it as ds dt times dt, what's happening here. This is velocity. This is in centimeters per second. This is little pieces of time. What are the units for time? Seconds. If you've got centimeters per second multiplied by seconds, what are we going to get? Centimeters. This will give us centimeters. The integral of velocity gives us position. Now, we sort of should have known that already, right? We're going to get the position. Okay, so let's figure out what this integral of velocity is. And I'll lose my head if it wasn't attached. No, I lose my red pen because I threw it up in the air. Okay, so the integral of t squared minus 8, can I write this as to the -1 power just to make it easier to integrate? T plus 1 to the -2. Well, all of that is times dt. And by the way, this is another sort of re-emphasis that the entire integrand, all of this, is times the differential. A lot of times students will write it this way, where they put the 8t plus 1 to the -2 and they just write dt, and technically that's wrong, right? Because this little piece of time is not multiplied just by that. It's multiplied by both of these. This is the centimeters per second times seconds, right? So make sure that whole, if there's more than one term, you have to have parentheses. If there's only one term, you don't have to worry about it, but there's two terms here. Okay, so let's integrate. This is going to be t cubed over 3 minus 8 t plus 1 to the -1 divided by -1. I'm going to add a c in just a minute. Let me clean this up. This is t cubed over 3 plus, right, minus is plus. There's an 8, and I'll put that down in the denominator, t plus 1 plus a constant. So this is now the general solution to the position equation. Right, we've got the position, but we don't know what c is yet. But they did tell us for this problem, s of 0 is 9. So let's put that condition in. S of 0. So s of 0, 0 cubed over 3, 8 over 0 plus 1, plus c. But wait a minute, I wrote s of 0. We know what that is, don't we? S of 0 is 9, because they told us this. Let's put that there. So now we get 9 is going to, let's see, 9 is equal to 8 plus c. So c is equal to 1. Okay, so c is equal to 1. Okay, so take that Hummer, put it back in the general solution. Now you have your particular solution, or your specific, sometimes they'll say that. So s of t is going to be equal to t cubed over 3 plus 8 over t plus 1 plus 1. Okay, and that gives us our position at any time. Now, if I were to, did they ask me to do anything with this? They said, what is the particle's position? Said find s of 1, find s of 5. Okay, well, if we've gone through all of this, we can easily get s of 1. You just plug 1 in there, so that's 1/3 plus 8 over 2 plus 1. I'll let you do the arithmetic. S of 5 would be 125 over 3 plus, we're putting 5 in there, what, 8 over 6 plus 1. So you could calculate s of any time that you want. But they gave us sort of a shortcut way of doing this. So let me go to the definite integral just for a minute. The integral from 0 to 1 of ds dt dt. Okay. S of 1 minus S of 0. I don't like that, Mr. Bosquet. What just happened? We'll go back to the fundamental theorem of calculus, way back in chapter 4, whenever you first did it. It said this, the integral from A to B of f prime of x dx was f of b minus f of a. Okay, so certainly you should be cognizant of that. We had a bunch of those on the test, on the semester test. If you got your semester exam and you didn't throw it away or tear it up in shreds, and you watched the video, there were 3 or 4 or 5 problems that dealt with the fundamental theorem of calculus. It's a real key piece in first semester calculus. So what do I have here? Well, f prime, I'm writing it this way. Maybe I could write s prime. I could do that, I suppose. ds dt, that's s prime. Okay. So s prime of t dt, and this is the a and this is the b. It just falls right in. Right? Okay, so if that's the case, and we're told, well, let's do one other thing. Let's take this s sub 0 and chuck it to the other side. So I have s sub 0 plus the integral from 0 to 1 of s prime is s, I guess I should be consistent here, s of 1. They told us this was 9. This thing is just a number. And you know what's good with numbers? What's the machine that does numbers really well? It's called a calculator. Let's find that number on here. So we've got 9 plus math 9. We dump in y1, that was our velocity, comma x, comma 0, comma 1. I've just calculated the answer to my problem, 5 1/3. That's what s of 1 is. S of 1 is 5 1/3. If I had gone through the trouble of working this problem out, right, trying to do all that calculations with common denominators and all that mess, let's see what happens. 1/3 plus 4, I guess 8 over 2 is 4, I know that, plus 1. Look at that, son of a gun, same number. Okay. I did not need the antiderivative to find s of 5. If I want to find s of 5 without doing the antiderivative, I can simply do the same drill. So let me do this. The integral from 0 to 5 of s prime of t dt is going to be s of 5 minus s of 0. And again, I'm sort of, some of these are cursive s's and some of these are Roman s's. I got on my trig class because they kept writing their s's and made them look like 5s. So I said, please do that for me. Okay. As long as you can distinguish between them, that's okay. So we chuck this across and we get s of 0 plus the integral from 0 to 5 of s prime is going to be s of 5. Right, notice the 5 looks like an s sometimes if I'm not careful. S of 0 was given to be 9. 9 plus this integral, well, this is just a number. Let's figure out what the number is. Okay, so we're taking 9, we're integrating the velocity from 0 to 5 this time, right? 0 to 5. Okay, so the position is 44. Notice it's a calculator problem. I don't need the antiderivative to do this. If I happen to have the antiderivative because somehow I could integrate this thing, and I somehow had written s of 5 was this number, right? And I wanted to actually figure out what number that was, and I can go through 125 divided by 3 plus 8 divided by 6 plus 1, and I get 44. See, I can find that position without finding the antiderivative if I have my calculator. Calculators are real good at doing definite integrals. Okay, one quick example. We're not going to get to example 3. Velocity is e to the x squared. S of 1 is equal to, I don't know, 102. Find S of 2. How do you do it? Can you integrate this? No, that was one of the ones on the test, right? You can't do it because that's not an elementary function. So you cannot get the antiderivative, but you can still answer the question. It's super easy on the calculator. You integrate the velocity, from what to what? What are the two times I got here? 1 to 2, and that's going to give me the position at 2 minus the position at 1. Do we know the position at 1? 102. So 102 plus this integral now, dt, is going to give us S of 2. And we can get this without finding the antiderivative. In fact, you can't find the antiderivative, but we can still answer the problem. I'll do this and then I'll let you bail. 102 plus math 9 e to the x squared, e to the x squared. Again, can't find that antiderivative. That's okay. Comma x, comma 1, comma 2. Bang, that's where I am at 116.989. Okay? If you have this problem of finding where you are given the velocity and given one position, it's a 10-second problem. Okay, let me let you go. Go back and look at your exam. I think there was 1 or 2 problems like that on the exam. And